So last day we have started the complexity analysis. We have seen complexity analysis of some sorting algorithms, and today we will see the sorting algorithms for many other cases. Complexity analysis for many other cases. But before that, uh, so we will start with the complexity analysis of linear search. So the first thing that we will do, just a minute. Complexity analysis of linear search. So the algorithm of linear search, you all know. We have a set of numbers stored maybe in some array, suppose. Some numbers are present, I am not going in detail. And the algorithm say that you start from here, this point, and keep on searching one by one element until you find out. So when now question is that what is the best case in this situation? Best case is obviously if the data that you are searching present in the first location. Suppose 5 is there and you are searching, search value is 5. So at the very beginning you will get the data. So that means best case means data present in the first location. And worst case can be something like, you can say that the data present in the last location. You will, if the number of total number of data is 10, then your 9 times you will miss. You will have a false condition checking. Only 10th time it will be true. Instead of 10, if it is 10,000, obviously it will take more time. So you can say that data present in the last location. Now if the data present in the first location, whatever the length of this array doesn't matter. If I assume the length of the array is n, so naturally time taken to search the element from n set of data, I can assume as t of n, which is representing time taken to search an element from n number of data. Now in case of best case, whatever the number of value n doesn't matter, I can see that since the data is present at the first location, so in the first attempt I will get the data. And this is what that means, I have a constant amount of time by which I can get the data in a best case. So that we express as b go of 1. Is b go sign. I'm sorry. B go of 1. Now why I am saying 1? The reason is that 1 is not exactly something like exactly 1. What I mean to say is that it will have some constant amount of time. Now it can be millisecond, can be microsecond, can be picosecond, can be anything. Doesn't matter. The unit doesn't matter. So this is what represents constant amount of time. Just a minute. So now, what about the worst case? That is important. This is very important. You see, in the worst case, obviously I can say that it depends on the number of elements, the time will increase. If I assume that for every checking it take 1 second, the algorithm take 1 second for every checking, that means to find the data which is present in the last location will take 10 seconds if the number of data is 10. If the number of data is 100, it will take 100 seconds. If the number of data is 10,000, it will take 10,000 seconds. So that means the time taken to execute the n number of data will entirely depend upon this n. And that's why I can easily say that Tn will be equal to big O of capital N in case of worst case. And this is for worst case. Right? Any question or doubt? Hello? Okay. Okay. So now let's go for complexity analysis of the other type of problems. Other type of problems may be, say, binary search, or maybe merge sort, or maybe quick sort. But you see, these problems that is left to analyze have a unique similar characteristic that both have, all actually have a recursive solution. So before we start analyzing, let's try to realize this one with a concept. That is what we call discrete numeric function. What is this numeric function? Let's write the definition first. If R is a set of real numbers a function whose domain in the set something like 0, 1, 2, 3 of non-negative integers and whose range is a subset of R called discrete numeric function denoted by AR. Okay, and so what is given that if R is a set of real numbers, a function whose domain is a set of this 0, 1, 2, 3 of non-negative integers and whose range in the subset of R called discrete numeric function. So discrete numeric function, that means it's a function which actually map one domain to another domain. And how we can visualize it? That if we have a domain or set A, in this side, as we have 0, 1, 2, n till n, and in other side there is a set of real number R, set R, where for each and every 0, 1, 2, 3 we will have some value that is a subset of this R, and these values may be say A0, say A1, A2, in this way AN, and these are actually, this 0 is related with this A0, 1 is related with A1, 2 is related with A2, like this. So this mapping from A to R, you can say it is the discrete numeric function which represents A to R. Now, what is an example of discrete numeric function? You can say, as an example, a discrete numeric function can be something like AR. I mean, for 0, 1, 2, 3, this AR can be something like 0, 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. I hope you can understand. I'm sorry, there is no 0, not 2 zeros. So I hope you understand, you can easily understand what this discrete numeric function represents. This is actually what we call Fibonacci series. Sorry. Where we can say that if you compare this one, and this one, this is some A of Ri. So let's write Ai only. So you can say Ai is equal to Ai plus 1. I'm sorry. I should not write in this way. Ai minus 1 plus A of I minus 2. Now question is that how you can represent this one mathematically. The mathematical form, the mathematical equation that we use to define, to express this type of discrete numeric function is called a recurrence relation. So the recurrence relation for this particular discrete numeric function can be something like f of n, some function over n can be written as f of n minus 1 plus f of n minus 2. You can say that this is a recurrence relation for the Fibonacci series. Always remember, each and every recurrence solution actually can be represented by a recurrence relation. What does recurrence solution means? Recurrence solution means the recursive solution. Because within this recurrence word we have a if you extract a subword, we have a option recur. This recur means it occur frequently. And this word actually came from the word recursion. So that's why each and every recursive solution can be expressed mathematically by some recurrence relation. So we will try to express the recursive solutions of the algorithms such as binary search, merge sort, quick sort with some form of recurrence relation. For example, let's try to understand how we can, what will be the recurrence relation, say for having suppose that I have a function fun, and within that um, we have something like okay, so let's see, let's write directly on that over there. Okay, don't need to এখন অবধি যা যা বলেছি বোঝা গেছে তো? Is it clear till now what we have discussed? Okay, okay. So now let's go for so first we will start with binary search. We all know what a binary search is. Still, let's have a very small recap on binary search. That if we have a number of data to search some element, we have a number of data over here. The linear search say that you search one by one, and binary search say that you first find the middle and check with the middle value whether the data is present or not. If you find the data is greater than the middle value, that means the data should be somewhere in the right side. But one thing is sure, before we start binary search, the data has to be sorted. That is why I can take the decision that if the data is greater than the middle value, then data definitely not present somewhere before the middle value. It must be present at least after the middle value till the end. Similarly, if we find a data which is lesser than the middle value, then we can give a surety that data is not present somewhere after the middle value. Data is definitely present somewhere in the before middle value. So basically what we do, but before that let me tell you one thing. What is the best case scenario for this? Best case scenario for binary search will be something like data is present at the middle that you are searching. So at the first attempt you will get the data. So the best case is that data is present in the middle position of the actual array. Now in case of linear search, the best case was little bit different. You see, it was somewhere in the first location, but in case of bubble search, binary search, it is somewhere in the middle. So depends on the algorithm, obviously the best case varies, but whatever, here this Tn will be same as it was big O of n 1, because it will take a constant amount of time. Data is present at the middle, just in the first attempt I will get. I don't need to see how much data set the large is. Now let's come for the worst case. The worst case is what situation? Let's try to analyze it. And suppose that I have some data present over here and they must be sorted, so I'm writing in a sorting, increasing order fashion. Suppose this 10 data is present and suppose you are searching 1, so your search value is say 1. So in that case what will happen? In the first attempt your total search space is basically the whole. You are finding the middle location, that is 5, and search value is lesser than the middle value. So what will happen? Next time your entire search space will be decreased to by half, and then again you will find something some middle and we will check it, and your again entire search space will be half of the half. And in this way you see you are actually minimizing your search space by n by 2, where n is the total number of data in the previous search space. So if you go for the algorithm, I hope you can remember that at the first time we had a declaration of a middle, that middle equal to lower plus upper by 2, so that I can check whether it is exactly the data is present in the middle or not. If it is not present in the middle, data is greater than the value of the middle position or lesser than the value of the middle position. So if I consider that obviously that line will take some constant amount of time, and after that if I go on decreasing this search space because of this worst case situation, so in this worst case scenario you can say you can define Tn by a constant amount for calculating the middle location. So constant amount of means C plus it will take time to search this half of the array. What I mean, ultimately you have to find out time taken to execute some search operation using binary search on the entire data set. So the time taken to execute this entire data set will be equal to finding the middle position plus the time taken to execute the searching 1 of this half of the part, because I can see that 1 is the search value which is not present obviously after 5, so I am decrementing search space by 2. So that means a constant value and time taken to execute the search operation for 1 on n by 2 amount of data set. By the way, so let's write it clearly. Tn will be equal to T of n by 2 plus C. Now question is that, yes, tell me. Why 2? Are you searching both spaces? You are entirely cutting down the, I mean, from here, this part, right? You are initially you had say 100 locations to search. What you are doing, you are decreasing your search space from 100 to 50, right? And that is why I have written T of n by 2. Is that clear? Okay. Priyanka, is it okay? Okay, fine. So that means the recurrence relation for a binary search can be written in this way, in a worst case scenario. Now question is that how we will define this T of n by 2? We don't have any idea to express this T of n by 2. But remember one thing, that T of n by 2 is nothing but time taken to execute the search operation of some value on n by 2 amount of dataset. So since the algorithm remains same, I mean, if I consider this is equation 1, and since the algorithm remains same, in place of T of n, if I write T of n by 2, that means basically instead of n you are writing n by 2, so automatically it will become T of, in place of n by 2, in place of n it will be n by 2, so it will become n by 4 plus c. So as if you forget about that you had this m search space. Forget about this. This is n and this is actually n by 2. This one. So assume that this is your input dataset. So if the input dataset you are defining as n by 2, obviously searching 1 in this dataset will be equal to finding the middle value and searching the half of this in a worst case scenario, which is basically n by 4 with respect to the original array. That's why I have written n by 4. This is say equation 2. Now if you put this equation 2 in equation 1, so if we put equation 2 in 1, we will get T of n will be equal to, instead of T of n by 2 I will write this entire thing. So T of n by 4 plus c, and another c is there that was already present in equation 1. So as a whole it become T of n by 4 plus 2c. So say this is equation 3. So you have written T of n in this form. You have also written T of n in this form. So let's now assume what is T of n by 4. If we consider T of n by 4, since the algorithm remains same, only instead of n I have n by 4, it will become T of n by 8 naturally. I hope you can understand. And a constant amount of value for finding the middle location. So assume that now this is your input array. So if it is your input array, obviously the time taken to find the search operation will be equal to finding the middle location and then searching the value within half of this array. Half of this array is obviously n by 8. If the input is n by 4, then half of the array will be n by 2, n by 4 by 2, that means n by 8. And that's why I have written this one. So now suppose this is equation 4. So if you place this equation 4 again in equation 3, so if you put 4 in 3, what I will get? I will get T of n will be equal to, here we had T of n by 4 plus 2c, and T of n by 4 itself is this one. So you can write T of n by 8 plus c plus 2c, because 2c was already present here. That is separately outside this T of n by 4. So as a whole it becomes T of n by 8 plus 3c. This c is the constant amount of time. I don't need to understand any unit, even I don't need to go through the exact value of c because it's constant. It doesn't depend on n. So now see, analyze, that means T of n can be written in this form also. So now you see, if you closely watch this different variation of T of n, expression of T of n equal to T of n by 2 plus c, then it becomes T of n equal to T of n by 4 plus 2c, then it becomes T of n by 8 plus 3c. I hope you can predict what can be the next one from here. The next one I can write T of n will be equal to T of n by 16 plus 4c, and next one will be T of n by 32 plus 5c, and so on continue. So basically what you are doing, as much denominator increases, the whole value decreases. So the total search space will minimize, as we have seen over here in this example. The search space minimizes, and a time will come where you have only one data in the set, and that is the middle, and maybe data is present over there or may not be, but you can then say directly the data is present or not present. That's all. Now to reach only one element segment, this part has to be equal to 1. So basically we are getting a pattern that if you check the denominators, this 2, then 4, then 8, then 16, then 32. So basically the pattern I can write T of n by 2 to the power I plus the same power, with the same power it is multiplied by c, so it will be IC. Now I can have a constant amount of time if I consider that I have a data set having only one element array, and I asked you that what is the where the data is say 7 present or not. So since there is only one element, you can directly say, you don't need to go through. So the finding whether data is present in this one location is constant. So that means a time will come when it will become 1. So if I consider that n by 2 to the power I equal to 1, so that means n will be equal to 2 to the power I. Now obviously I don't know what is value of I. In which iteration ultimately my data set will reach in a situation where I have only one element in a segment, I don't know. So that means I have to find out what is equal to I. Now how we can do this? If I put a log over here, if I just put log in both sides, naturally this one will become I log 2. Obviously log is base 2. So it will become equal to I. So that means I will be equal to log n. Now if you put this one over here, since we have assumed that obviously I have to reach some situation where it will be equal to 1, so basically it is T of 1. That is time taken to find the search operation, time taken to execute a binary search on only one data. That is T of 1. Plus the constant will be multiplied with log n. So C log n. Now in the last day we have seen that for a very large value of n, the constant value doesn't have any significance. So what we do, we basically omit those constant values when we express the class of the function. So from this expression T of n, we can say definitely this constant value will be vanished, and this C will also vanish because it's a constant value. So here from here I can easily say that T of n will follow order of log n. So this is the worst case time complexity of binary search in worst case. So if you compare the worst case time complexity with linear search, you will see that in case of linear search it was big of n, and in case of binary search it is big of log n. If you take a calculator and if you check these values for different value of n, you will see that if you put a graph over here, a graph having n and here it is time, the linear search will follow a fashion something like this, linear fashion. This is linear. And in case of binary search, it become something like this. This is binary search. So naturally you can say from this graph, since this curve is measuring the performance with respect to time, you can easily say that binary search is better than linear search. So any question you have regarding what we have discussed till now? So this is clear, right? For both of you. That's very good. So now, just a minute. Just a minute.